Welcome to The Critique. We're looking today at part 4 of the submitted work, which gets into analytics and big data, how to define, understand, and really apply those advanced techniques to these huge, varied data sets. We want to make sure it connects strongly with modern CS realities. Let's jump straight into the feedback. So one thing that comes through clearly is the categorization approach. Basic, advanced, operationalized, monetized analysis, laid out in that table. And the advanced section really digs into predictive modeling, things like classification trees, logistic regression, standard stuff.
That structure is definitely there. It's logical. But I did find myself wondering, how do these ideas of advanced analytics, which seem pretty grounded in, well, traditional data mining, how do they really hold up against the sheer scale and speed requirements of big data? It's a different beast now, isn't it?
And that brings us right to our first critique, which is about the angle and originality. The current discussion, while, mathematically sound on advanced analytics, it maybe relies a bit too much on definitions, classification, prediction that sort of predate the big data explosion.
Yeah, the weakness there, I think, is that framing might downplay how fundamentally different the analytical challenges are now. We're talking petabytes, that's volume, and high-speed streams, velocity. The current text explains what the models do, sure, but not really how the whole environment, the architecture, changes the game. The stats might be similar, but the problem context, totally different.
So, to give it a sharper, more original angle, we'd suggest focusing less on what the models are doing, like predict or classify, and more on the how. Specifically, how does the analytical architecture itself need to evolve to handle this throughput, to get outcomes that just weren't possible before? It becomes less about stats and more about distributed system strategy.
Right. We need some concrete examples that really hit home the scale aspect. Force the reader to think architecturally. So maybe fewer generalized data mining examples and more focus on the unique challenges of, say, real-time decision-making at massive scale. You could talk about algorithms needing to run fast enough, deep enough, on constantly growing complex data sets. That's cutting-edge research right there, elevates the whole discussion.
Exactly. Or another angle could be problems where the sheer volume and dimensionality just break the old methods. Think about complex spatial data analysis. You could bring in spatial databases, OGC standards, the Open Geospatial Consortium stuff, or network analysis using something like Jung, that Java graph framework. The challenge isn't just running the model, it's how you even define the problem with billions of nodes. It forces a totally different analytical design, grounding advanced analytics in today's computing world.
Essentially, yeah. It's about moving past just applying old models to bigger data. It's about how the infrastructure constraints and the sheer scale create entirely new analytical problems that demand, well, architectural innovation.
That discussion of scale then naturally flows into the issue of data quality, especially with high-velocity data. The material does a good job introducing this warning that big data can be dirty, low signal-to-noise ratio, all that. And it rightly points out that your cleaning strategy depends on the goal, like the spam filter example, where dirty is the signal.
Okay, I get the point about context-dependent cleaning. But is it always enough? I mean, think about these massive, unstructured sources. Social media, sensor data streams. They're inherently volatile, noisy. Is just front-loading the quality checks or validating after the fact really sufficient for ensuring truthfulness, for veracity?
Which leads to our second critique, focusing on completeness and focus around that veracity aspect. Right now, veracity, how accurate, how truthful the data is, seems positioned mostly as a pre-processing thing, or maybe a post-analysis check, like validating a small sample after you've done your exploration.
The gap we see here is that this kind of overlooks the need for the models themselves to actively grapple with noise and bias while processing these messy, low-veracity streams. You can't just hit pause on a petabyte stream to clean it perfectly, right? The system has to be built to handle that uncertainty on the fly.
So the suggestion here is to really weave veracity into the analytical methodology itself. The model needs to be designed to actively mitigate noise, to establish some kind of probabilistic certainty. It takes it beyond basic data hygiene into, well, more sophisticated analytical design.
Then you could make this really concrete. Maybe contrast it with something like the IBM Watson approach. Watson uses evidence-based learning, generates hypotheses, then refines them using probabilistic scoring based on all the incoming info. That's fundamentally different from just running a deterministic classification tree, isn't it?
Totally different. A standard classification tree kind of assumes clean input and spits out a definite answer. A is B. But Watson and systems like it, they're built for messy input. They output something like A is likely B with a confidence score. Showing that contrast really highlights how modern big data analysis has to deal with uncertain inputs. It's a necessary evolution.
Or another great example, correlation verification. Instead of just trying to clean, say, Twitter data reporting local rain, you show how you'd cross-reference that low-veracity stream with high-veracity data, like actual weather satellite images or telemetry. Building a truthful picture becomes an analytical modeling task itself, not just a cleanup job beforehand. It shows veracity isn't static, it's something you model dynamically.
Excellent point. Okay, so moving from those conceptual hurdles of scale and veracity, let's talk about actually doing the analysis. Chapter 14 discusses customized big data analysis. It maps out a path from flexible low-level tools R, Jung for graphs, TALib for finance, towards these higher-level abstraction frameworks meant to simplify things like continuity app fabric or open chorus.
Right. And that trade-off when you're scaling up performance via direct control versus faster development via abstraction, that's a huge decision for developers. Is the connection between, say, picking R for a custom job and then maybe adopting app fabric later, is that leap fully explained? Because operationally, those are worlds apart.
This is our third critique, then, about structure and flow, specifically the pacing. The material seems to jump quite quickly from talking about flexible, maybe more code-intensive tools like R, which is great for prototyping, custom analysis, straight to the benefits of abstraction layers, these unified APIs that hide the complexity.
And the weakness, we felt, is it skips over the nuance of the trade-offs, specifically in a big data context. A technical audience really needs to grasp when that low-level flexibility is absolutely critical, maybe even a competitive edge, versus when the abstraction layers offer enough value in terms of speed to market or ease of use.
Choosing wrong here can be incredibly costly on large projects.
So our suggestion is to introduce a clearer decision framework and maybe center it specifically around latency and complexity. Make it clear, when do developers have to get their hands dirty with the underlying infrastructure? Hadoop, MapReduce, HDFS directly? And when is it okay, or even better, to accept the potential overhead of abstraction for the sake of development speed or maintainability?
Latency is definitely the key metric to focus on. You could use the distributed computing model, explain how MapReduce works in parallel, and why for certain applications needing ultra-low latency, think high-frequency trading where microseconds count, or real-time prediction models on edge devices or EC2 writing to a high-level API might just add too much delay. That abstraction layer isn't free performance-wise.
Precisely. Explain why teams sometimes spend ages optimizing at the lowest level. Then, you can properly justify the high-level frameworks. App Fabric, Open Chorus, they make sense when things like deployment speed, team collaboration, maybe deploying across different clouds or hybrid environments, when those factors outweigh the absolute need for that last microsecond of optimized performance.
But maybe add a bit more texture to that decision too. It's not just raw speed, right? What about maintainability? If you build a super optimized MapReduce job, is it going to be maintainable in 5 years when the original developer is gone? Often the answer is no. So framing the choice around complexity, long-term maintenance versus pure speed gives architects really practical guidance. That resonates with experienced CS folks.
Okay, so this has been a deep dive into refining the core ideas around big data analytics architecture. The goal is really to make the definitions, the examples, the architectural discussions feel much more grounded in the realities of today's high-scale, high-velocity world.
Yeah, so just to quickly recap the 3 main areas. First, refresh the angle and originality. Move the definition of advanced analytics forward. Focus less on what models predict, more on how architecture enables new things, using examples based on scale and dimensionality.
Second, boost the completeness and focus on veracity.
Don't just treat it as cleaning. Integrate it into the models themselves using probabilistic methods, cross-verification, build trust into the output directly.
And third, strengthen the structure and flow around tooling choices. Create that clear decision framework, contrasting low-level control like R, MapReduce, with high-level abstraction like AppFabric, using latency, complexity, and maintainability as the core trade-off.
These are all significant, actionable points that we think will really enhance the material's impact and relevance for the intended audience. We definitely encourage you to work these suggestions in, refine the piece, and please send the updated version back to us for another look. We're keen to see how it evolves.